So, hello everyone. I hope you can hear me well. My name's is my sound okay? Just before we start. All right, good. So, I would like to welcome you all to my presentation on boosting mixed signal design productivity with FPGA-based methods throughout the chip design process. My name is Gabriel Rutsch and I'm working for Infineon Technologies. Emergent trends like autonomous driving, the electrification of the car, and the idea of shared, connected, and over-the-air updated cars are disrupting the automotive world. Due to that, there's a significant increase in application heterogeneity, the diversification of the applications, and also a higher need for connectivity. In order to address those changes properly, an analysis and verification platform is needed that enables high-performance simulation of analog phenomena in variable levels of accuracy and detail in the context of an entire application. Just a quick overview of my talk. I will start with a brief introduction, then I will go into detail about some related work activities. I will give you an overview of the application that we targeted here, and also the two FPGA-based prototypes that we developed through this case study, show the results, and then have a short conclusion. So the first question we wanted to answer ourselves is, does it make sense to use FPGAs for analysis and verification of analog mixed signal chips? And if so, what's the impact on overall design productivity? Here, design productivity means how efficiently and effective a certain method performs for a specific task. Some of the key challenges that we had to address when we entered the mixed signal emulation domain was, on the one hand, configurability. Compared to a CPU-based simulation platform, you need to make sure that parameters are runtime configurable. If they are not, then you have to synthesize again every time you change a certain parameter setting. Another challenge is scalability with respect to the method that you use in order to map the behavior efficiently on the FPGA's resources. So the question is really, am I currently using a single point solution that solves this one specific problem, or can it also be applied to a broader range of different applications? Another important aspect is resource utilization. And since we're targeting medium to small sized FPGAs, this is more critical compared to, let's say, a proprietary emulation platform. And typically, there's a trade-off involved between the simulation throughput that you could achieve and the resource utilization that you need in order to represent a certain functionality on the FPGA. In order to address those challenges properly, we made use of two Python-based open source tools. One's called MSDSL, and this one was used to generate synthesizable function models. And the other one is called NSMod, which was used to automate everything with respect to the FPGA. During the course of our case study, we developed two FPGA-based prototypes for a smart magnetic sensor that is used in automotive applications. Now let's have a look at some related work activities. Frank Nothaft has already shown the benefits of using hardware emulation. In this case, he was using a proprietary emulation platform for embedded software development on the example of a large cellular modem. Now, compared to him, we don't target a proprietary emulation platform. Rather than that, we focus on a portable and low-cost FPGA board. On top of that, we also try to evaluate the benefits from using this kind of a hardware emulation platform for as many different activities throughout the chip design process. Simone Fontanesi has already shown in the past how to get from a conceptual System C-based model of the digital core only of the smart magnetic sensor to a synthesizable RTL code using high-level synthesis. This is kind of the starting point for our work here. And on top of the already existing method, we also add a methodology how to automatically translate analog functional behavior to synthesizable formats. On top of that, in order to improve reuse and reconfigurability, we introduce kind of an abstract model specification layer. The application itself, or the numerous applications for this product, can be seen here. There are two major categories. On the one hand, it's used for sensing a position, and on the other hand, the sensor is used to sense speed. And for both of those categories, there are numerous areas in the car where this can occur and make sense. On the bottom right, you can see an example of how it is used within an ABS application. Now, the spinning component has a magnetic encoder wheel closely attached to it. This is the red and blue round area on the surface. Very closely to that is the sensing element itself, connected as satellite to the rest of the application. A quick overview of how this application could look like as a whole. On the left, we have the magnetic encoder wheel that is generating the speed and direction information that is sensed through the sensing element, which is already part of the ASIC. And then this information from the sensing element is passed through an analog front end to the digital backend, where some post-processing happens, like computing kilometers an hour, checking some safety features. And then this information is passed again through the analog front end, typically via current and or voltage modulation to a local ECU. This ECU is already part of the customer system and does some further post-processing. Eventually, it's also connected to the main control unit of the car, for example, via CAN or LIN. Before I go into detail about the two FPGA prototypes, I would like to spend some words on the two frameworks, point out the most important features there. So as I said before, MSDSL is used to generate the synthesizable function models. And one of the key aspects that make it convenient to use for that is that you can make use of a system Verilog library that enables a seamless transition from a fixed point to floating point representation of the arithmetic operations. This is quite convenient when you do model creation, because there you can really focus on the core functionality first, using floating point data types. And once the model does what you intended to do, then you switch automatically to a fixed point representation. You deal with overflow and precision loss issues, and then you can map it on the FPGA as well. Being able to quickly change from fixed to floating point representations of the functionality also means that it's easy to, let's say, optimize and regulate how many resources are needed on the FPGA. Because typically, fixed point arithmetics can be represented on FPGA with a lot less resources needed. As I already mentioned, we made use of an abstract model specification layer that eases reuse and reconfigurability of the models. And on top of that, especially in order to also represent more complex behavior in a compact way, we support different modeling styles. As an example, this means that you could either, let's say, put down the equations one by one and assign them to certain variables in the model, or you can just provide a system of linear differential equations, and this will be solved automatically by the framework. Or you can use a representation that is similar to a SPICE netlist, where you make use of basic components. This also makes it convenient to optimize your model towards either pin accuracy or simulation throughput. And last but not least, vendor neutral RTL is being generated, which means that you can also use the models quite easily when you want to map it to a different hardware platform. NSMod, as I mentioned before, is automating everything related to the FPGA, which includes setting up the project, generating the bit stream, inserting some additional instrumentation for tracing and simulation control. And on the other hand, it also allows to seamlessly switch from an RTL simulation to an FPGA simulation. That's quite convenient when you start setting up your tests. Typically during that stage, you don't want to do this on the FPGA. Rather than that, you develop your test case on the CPU, and then when you really want to run the whole test suite, you move to the FPGA. In order to do that, there's a Python layer available that allows interactive control of the FPGA simulation itself. So what you could do, for example, is pause this simulation after a certain amount of time, then read and write signals in the design, and then continue the simulation. I would like to start with the FPGA-based hardware-in-the-loop prototype. Here we have some external hardware also as part of the application, and an overview of the lab setup you can see on the top left. On the right of that picture is the spinning component with the magnetic encoder on this, the top surface, and quite closely attached to that is the sensing element, which again is connected to a power board, or you could also call it adapter board. There's some auxiliary circuitry either on the sensing elements PCB or the power board that account for some parasitic effects that are due to the shape of the prototype. So in some setups, the sensing element is connected to the power board via cable, for example, and there you need to have an additional amplifier stage. And the standardized communication interface to the local ECU was also represented as discrete hardware, since this is not going to change depending on the reference design of the customer, for example. Then on the bottom left, we have the FPGA board that we made use of. It's an RTX chip, and it's a quite small footprint, which were the two main aspects that why we chose that board. Now, anything about the application that I didn't mention yet is put on the FPGA and represented with a synthesizable format. Starting from the left, we have the speed and direction signals coming from the sensing element. Those signals are still purely analog. We made use of the x86 IP cores on the Xilinx FPGA to translate this into an integer. And then we translated the integer to a fixed point data type, which then is being used in the analog front-end section, which is the biggest one in the middle, to do the arithmetic operations for the basic functional blocks. Those include compensators, comparators, some amplifier stages, and are typically dependent on the application and also the reference design. So those are the components of the design that you want to keep flexible. This is why it makes sense to have them configurable on FPGA. On the very right is the digital front end, and in the end, digital PWM signal is sent to the current interface in this case to communicate to the local ECU. Now, the whole analog front end and digital front end here that I showed before is also part of the second prototype called FPGA-based simulation prototype, and is represented with the grayish area here. So it's a one-to-one mapping. I will not go into detail about this anymore. Besides that, we also added a sine wave generator that is accounting for the spinning component that is lacking in this example. And this one is configurable from the host PC through some additional instrumentation, which I mentioned before. And this, for example, allows you to pause the simulation. The way this works is that you use a certain control I/O for that. You set the control mode. This signal is interpreted by the control unit, which is then recognizing, okay, I need to pause now. This sends a 0 time step request to the time manager, which is computing the smallest next time step that is requested, which is 0 in this case. And this will gate all the clocks in the clock manager to the design, which freezes the simulation, but still allows you to read and write values from the application, or also dump the trace to the host PC. Now, in order to evaluate the capabilities of this FPGA-based simulation prototype, we had a look at two real-life test cases. They're quite different from one another. The one on the left is called normal rotation. It's quite static, and this is typically what can be observed by the sensing element if the car just moves forward without any acceleration. The other one on the right is called rotational vibration, and this is a typical case for that is when the car stops. Rotation is being generated, and this can be observed in the speed and direction signal as well. The theoretical throughput of the FPGA simulation is significantly faster compared to the CPU simulation. In this setup, it's about 12,500x, which is also typically observable in other research activities. But since we're working on FPGA-based platform, there are several different aspects that need to be considered on top of that. And one of the most obvious ones is that, of course, you also need to generate a bit stream. This took about 25 minutes in this example, which is quite a long time. And depending on your use case, this might even mean that it doesn't make sense to use an FPGA, especially for quite short running simulations where you don't run a whole lot of them. It might just not be the right platform to use. On the other hand, there's also an additional communication interface between, in this case, the host PC and FPGA that induces some additional I/O overhead. The simplest solution how to communicate from the host PC to the FPGA, in the case of Xilinx FPGA, is to just use the built-in virtual IOs. However, they introduce quite a lot of latency to the overall system. So a read takes about 130 milliseconds and a write even more, 360 milliseconds. And especially if you have a dynamic test case where you quite often need to communicate between the hosting PC that is scheduling or running the test case and the FPGA, this adds a lot of simulation time on top. Luckily, there's typically a set of alternatives available on FPGA board. One of the most typical ones is just to use the USB UART interface. In our example, this already reduced the latency introduced by this additional communication interface by 2 orders of magnitude, which is great. And since we make use of fixed point arithmetics and also the simulation results are represented as fixed point data types, those are not quite convenient to interpret in the end. And it does make sense to do a conversion to floating point later on, which needs some additional compute time. And depending on the number of signals that you want to trace and the number of samples for each signal, this can be quite significant as well. So it's not really the best platform to do system debugging. Now let's have a look at the results from our 2 test cases. The left is the normal rotation, on the right is the rotational vibration. Simulation time itself was quite short, roughly 40 milliseconds. Bitstream generation, as I said, 25 minutes. Then you need to account for some additional time to launch the simulation. On the CPU case, this is typically reading precompiled objects and elaborating the design, anything that is necessary in order to start the simulation. On the FPGA, this means starting the framework, programming the bitstream, and initializing some of the additional instrumentation on the FPGA, which does take quite some time if you use the standard Vivado tooling. Then, since parameters are runtime configurable, this also needs some time to initialize those values. And the effective simulation time itself was quite short on the normal rotation test case and quite long on the rotational vibration. And this difference is really due to the I/O overhead. In this case, we made use of the virtual IOs. Post-processing didn't take a long time here, since we only traced between 5 and 10 signals and only had about 32K samples for each signal. That results in an overall simulation time of 37 seconds. For the normal rotation, almost 54 seconds for the rotational vibration, and about 270 for the CPU-based examples. And here you can see that this increase that we could theoretically get about of 12,500x is really not visible here anymore. And I think this is one of the most important takeaways, that you really need to find the sweet spots of where it makes sense to use an FPGA rather than a CPU-based simulation platform. This is what we try to do next. This is what we did next. We assessed the different activities through chip development on the example of the magnetic sensor. So one of the quite early stages of chip development is the product definition phase. And during concept studies, one of the big objectives is to find suitable applications for your product. And this means on the one hand that your product or your concept of the product still needs to be configurable, but also the application itself should be. And this means that having a virtual simulation platform available makes more sense rather than a hardware-in-the-loop setup from the start. And since you run a lot of different variations of the parameters, you have a large set of simulations at hand, and this also makes sense for using an FPGA. On the other hand, when you start discussing requirements with a customer, it's also convenient to have fast turnaround cycles and identify quickly or conduct proof of functionality and make sure that the concept that you have in mind can address the requirements properly. But you can only get to a certain level of confidence with this purely virtual environment, which means that at one point when the concept is quite settled and you have an application that you want to focus on, it does make sense to have a hardware-in-the-loop setup available too, where you can show the customer side, for example, that your concept is also interacting properly with the reference design of his. On the other hand, on your side, you can have a hardware proof of application, and it's quite convenient. What I showed before, that you can just drag the core that is synthesized on the FPGA from the hardware-in-the-loop prototype to the simulation environment. You can also do this the other way around. So getting the hardware-in-the-loop setup up and running doesn't imply additional modeling efforts. This is different if you started from a CPU-based environment, because there you don't need to make sure that the model is synthesizable. During pre-silicon verification, one of the key objectives is to verify as much of the product's functionality as possible in order to circumvent potential redesigns later. And a typical verification strategy for this kind of product would include about 10,000 simulations. Considering sequential execution time, since parallelization is possible on a CPU and FPGA-based platform quite conveniently. This takes about 30 days on a CPU, and here we can really see the benefit from having an FPGA-based simulation environment, because this only takes 5.25 hours. Here we made use of the USB UART interface, so the latency introduced by the additional I/O interface was quite short, quite small. Also, during post-silicon verification, we did find some use cases where it makes sense to apply an FPGA besides the conveniency of having a quite performant simulation environment. For example, for ATE test pattern or production test pattern development, and also for lab automation, lab verification test development. The FPGA was also some kind of an enabler for different activities. So you could start with setting up the production test environment or the application test environment several weeks earlier, since you didn't need silicon available for that and could just use the FPGA hardware prototype. On the other hand, also it's convenient when you have some additional customer opportunities at this point in time, since one of the first activities or questions from the customer is, how well does your product perform in exactly my reference design? And this implies that you need to verify your product for a different magnetic operating point. There might be some stray fields, or there might be a different geometry of the wheel, or the orientation of the sensor is different. This means that you need to run the whole pre-silicon verification test suite again with some different parameter settings. On the other hand, it also allows the customer to use the FPGA-based prototype to define or develop his own ECU early on. As a short summary, in this case study, we presented we evaluated the impact on AMS chip design productivity of a magnetic sensor when applying FPGA-based prototyping techniques. The key challenges in the domain of AMS emulation were addressed through open source tools, and we developed 2 FPGA prototypes for the application, which we also used during several stages of the chip design process. That concludes my talk. Thank you for your attention, and I would be happy to answer some questions.
Many thanks, Gabriel. So do you have questions for Gabriel now? You can also raise your hand in your chat, or can also provide your question in the chat. Maybe we can start with the first one, Gabriel. So you showed this approach. So how was you have also already studies concerning the complexity? So how complex can be a design so we can handle this in the this flow?
Okay, so we did apply this approach to several different products, spanning from switch mode power supply to a PCI Express 4 or USB-based PHY. We had models that required variable time step and also needed to manage, let's say, bidirectional data flow to a certain extent. For example, in a flyback topology, where you wanted to observe the current from primary to secondary and back. So there's a lot of different modeling challenges that were already addressed. The level of detail was rather, let's say, abstract. For some of the products, it was pin accurate to the application, to the implementation that was used for proof of implementation purposes too. But yeah, I mean, the biggest limitation is that you only have so many resources available on the FPGA.
That's really good. So do we have further questions? So we have the chat. So from Jacob, how easy is this to scale up to a large community to develop, given the FPGA is getting very expensive when they are getting larger?
I mean, what you can observe is that there's a trend for also FPGA-based cloud computing. And you could think of something similar here. In our case, we target rather small FPGA boards right now. They cost about $200, and that's not a big deal to just order a large bunch. But I mean, your concern does make sense. And an alternative here would also be to use a proprietary emulation platform that can also be, let's say, used as kind of in a cloud-based setup. That is already the case in our development environment. So I think there are ways to scale.
Okay, so there is also some kind of trade-off between using simulation and also FPGA or emulation, right?
Come again?
So there is also kind of a trade-off when to use simulation, FPGA, or emulator. So this is
Yes, definitely. So I mean, cost is a different, very significant differentiator. On the other hand, especially if you want to trace more signals or you have to trace for a longer duration of time, this is really where an emulator shines. I mean, this is why they have this additional instrumentation around the Xilinx chips in order to allow that. And they have a quite convenient software stack to enable tracing entire systems for a long period of time. However, one of the things that you cannot do that easily with an emulator is really have a hardware in the loop setup. This is one of the reasons why we targeted for rather the smaller FPGAs.
okay. Thank you. So we are running out of time. So many thanks, Gabriel, for your talk. There are also other questions from Peter and for Jacob. So please try to contact Gabriel later in our video tour sessions. I guess it's a very interesting topic. So, but like to thank you again very much, and then go to the next talk.